So in this question, we have a radioactive nucleus, called nucleus A, that is initially at rest, but then it decays into three different particles. It decays into a neutrino, it decays into an electron, and another nuclear B. So the electron and neutrino are emitted at right angle, and they have their own respective momentums. And we need to determine the magnitude and the direction of the momentum of the second nucleus, so the nucleus B. So this can be done with the conservation of momentum because this is an isolated system. So that means that the vector addition, the initial momentum of 0 is equal to the final momentum, so final addition momentum of these three different particles. In other words, the vector addition of these three momentums, so momentum of the neutrino, the electron, and B, they should add up to be 0. And that also means that the two components, if we decompose B into two components, the components along the direction of neutrinos, the components along the direction of the electron, they will be equal and opposite to the momentum of the neutrino and the electron. And it's great that the neutrino and electron are perpendicular, so that means it's orthogonal. So we can decompose B into, we can project B into the two different components on their directions. So let's just, for the matter of convenience, assume that the neutrino is moving in the x direction and the electron is moving in the y direction. Then we have, say this is P. We have the x direction momentum equals the momentum of the neutrino equals 6.2 times 10 to the negative 3 kilogram meters per second. And the y direction equals this equals the momentum of the electron, so that is 9.6 times 10 to the negative 3 kilogram meters per second again. Now we can find the total momentum. We need to find both the magnitude and the direction. For direction, we can find it just by, say, call this angle theta. We can try to quantify the direction by finding this theta. So the magnitude P equals square root of px squared plus py squared equals 6.2 times 10 to the negative 3 square plus 9.6 times 10 to the negative 3 square kilogram meter per second. And this turns out to be 1.14 times 10 to the negative 22 kilogram meters per second. So that is the momentum of this nucleus. What about the angle? So for theta, we can find the tangent of theta. Theta equals arctangent of the momentum of the neutrino over the momentum of the electron over the momentum of the neutrino. So this is arctangent of momentum of the electron is 9.6 and momentum of the neutrino is 6.2. I am ignoring the 10 times negative 23 kilogram meters per second because it's the same in the denominator and the numerator. This gives us an angle of 57 degrees. So theta equals 57 degrees. So a better way to describe it would be that the momentum of the second nucleus has a magnitude of 1.1 times 10 to the negative 2 kilogram meters per second. It has an angle of it has an angle of 147 degrees from the electron's momentum, or we can say it has an angle of 123 degrees from the neutrino's momentum. So that is a good way to describe both the magnitude and the direction of this nucleus.